All right, guys, we're going to start right here by simplifying these logs. Set them each equal to a variable, and then solve. So the little ducky ducks under, the log floats away. I have 2 equals 2 to the a. That's 2 to the first. So cancel, cancel. I get a equals 1. Then again, the little ducky ducks under, the log floats away. I have 4 equals 2 to the b. 4 is 2 squared. The 2's cancel, and I get b equals 2. Finally, the little ducky ducks under, the log floats away. 8 is 2 cubed, and you end up with c equals 3. Now stick with me here. Would you agree with me that 1 plus 2 equals 3? Well then, using the variables that we've established from these 3 problems, we could say that a plus b equals c. But then looking up higher, remember that a was log base 2 of 2. So I could say log base 2 of 2 plus log base 2 of 4 equals log base 2 of 8. And then finally, I could say that log base 2 of 2 plus log base 2 of 4, well, 8 just so happens to be 2 times 4. Coincidence? No, obviously not. There's something bigger going on. Let's figure out what it is. If I rewrite this equation in generic terms, I get log base a of b plus log base a of c equals log base a of b times c. The math that I've done so far to lead up to this property is definitely not a mathematical proof, though. So that's where I need to go. We need to prove this property. Let's prove that log base a of b times c equals log base a of b plus log base a of c. And by the way, don't be intimidated by the word prove. This isn't a 2-column geometrical proof. It's basically like the derivations that we've done all year long, except this time I'm telling you what the answer is to start off, instead of us working our way into the answer. We're going to start this proof by saying that log base a of b equals something. We're going to say that log base a of b equals m, and then we're going to say that log base a of c equals something. We're going to say that log base a of c equals n. Then we're going to turn each of these into exponential notation. So the ducky ducks under, the log floats away. We get b equals a to the m. The ducky ducks under, the log floats away. We get c equals a to the n. I remember one year hearing a student practice this proof, and they got to this point and they kept saying, "Bam can, bam can," and that's kind of stuck in my head ever since then. Now I look back at the original proof. The proof involves b times c, so that's what I'm going to do at this point. I'm going to say b times c equals a to the m times a to the n. And this is where it's important to remember again that I'm just going to add those exponents, a to the m plus n. Cleaning this up a little bit, I get b times c equals a to the m plus n. Now we're currently in exponential notation, but if I take this back to logarithmic notation, here's the ducky with the leaf on his head, the ducky ducks under, the log floats back over, I get log base a of b times c equals m plus n. But remember, m was just log base a of b, and n was log base a of c, so I can rewrite this one more time as log base a of b times c equals log base a of b plus log base a of c. And that's the end of the proof right there. Now using words, we can see that as long as the bases are the same for every single log, 2 logs that are being added can become 1 log involving multiplication. Again, 2 logs that are being added becomes 1 log that involves multiplication. I like to remember this by thinking of a plus sign, but then I turn it slightly to one side, it becomes a multiplication sign. Multiplication, turn it slightly, becomes a plus sign. You can just kind of go back and forth and back and forth. Now, let's go back to where we started. You guys remember all of this? Would you agree with me that 3 minus 2 equals 1? Now, using these variables, we have c minus b equals a. Going back up to the top, we could say that's log base 2 of 8 minus log base 2 of 4 equals log base 2 of 2. And then one more time we could say log base 2 of 8 minus log base 2 of 4. Well, 2 just happens to be 8 divided by 4. Again, coincidence? I think not. It is a property that we can prove. We are going to prove that log base a of b minus log base a of c equals log base a of b over c. So here we go. Before we get there, however, let's remember that when we're dividing terms that have the same base, say x to the 7 over x to the 2, you subtract the exponents. That's going to be x to the 7 minus 2. We would have x to the 5. 10 to the 10 over 10 to the 3 is going to be 10 to the 7. In other words, a to the b over a to the c is going to equal a to the b minus c. This proof very closely mimics the proof that we just did. It starts by saying that log base a of b equals something. We've got log base a of b equals m. And then log base a of c equals something. We'll say log base a of c equals n. We're going to turn these into exponentials, so the little ducky ducks under. And again, we get b equals a to the m. The little ducky ducks under. We get c equals a to the n. And once again, you see, bam can. Now in the original proof we were dealing with b times c. This time we're dealing with b divided by c, so that's what I'm going to do. I'm going to say, well, b divided by c is a to the m over a to the n, and because those bases are the same, I can subtract the exponents to get a to the m minus n. So cleaning it up a little, I have b over c equals a to the m minus n, and we're currently in exponential notation. Let's take it back to logarithmic notation. So the little ducky ducks back under, the log floats back over. I get log base a of b over c equals m minus n. Substituting m and n out, I get log base a of b minus log base a of c. With this property, again, you can see that the bases are the same all the way through, and you can see that two logs that are being subtracted can become one log involving division. Again, two logs that are being subtracted can become one log involving division. Again, I like to think of it as subtraction becomes division. Subtraction becomes division. Subtraction becomes division. Those dots just appear or disappear. There's one more really important log property, and for that one, we're going to start here. Let's simplify each of these logs. So we'll say this equals a, and we'll say this equals b. See what you get. The little ducky ducks under, I get 4 equals 2 to the a, so I have 2 squared equals 2 to the a. I've seen this before, a equals 2. This log's a little more interesting. The ducky ducks under, the log floats away. I get 4 cubed equals 2 to the b. I could do the math on 4 cubed if I wanted to, or I could say that 4 is 2 squared, and then I can multiply these exponents. I get 2 to the 6 equals 2 to the b. Cancel, cancel. I get b equals 6. So now would you agree with me that 6 equals 3 times 2? In other words, b equals 3 times a. And if I go back to the original names for these variables, I have log base 2 of 4 cubed equals 3 times log base 2 of 4. Notice that exponent. An exponent up on a log can hop itself down to the front of the log. The property is written as log base a of b to the r equals r log base a of b. I've always imagined the variable r as a little froggy sitting on the log, and that froggy just goes ribbit and jumps off the front and goes ribbit and jumps right back up on the loggy, ribbit, jumps off, ribbit, jumps on, and that's what you see with the variable. R can jump off to go in the front, or r can jump ribbit right back up on top of that loggy there. That's one more property that we need to prove, but before we do, I'll remind you of a skill that we used just a minute ago. When you have a base to an exponent raised to an exponent, you multiply those two exponents. Again, 5 to the 9 to the 10 would equal 5 to the 90. In other words, a to the b to the c is going to equal a to the b times c. So now let's go ahead and prove that log base a of b to the r equals r log base a of b. Just like the first two proofs, we said that log base a of b equals something, and we called it m. We turned it into an exponential, the ducky ducks under, and we get BAM. Now there's no can in this one, it's just BAM by itself, but we look back at what we're trying to prove, and originally the first proof was b times c. The second proof was b over c. This proof is b raised to the r power. So that's what we're going to do. We're going to say b equals a to the m, but then we're going to raise both sides to the r power. A to the m to the r equals a to the m times r. And cleaning it up a little bit, we get b to the r equals a to the m times r. Now we're in exponential notation and we need to go back to logarithmic notation. So the ducky is going to duck back under, the log floats over, and so we have log base a of b to the r equals m times r, but the commutative law of multiplication says that m times r equals r times m, and then we can simply replace rm. So we have log base a of b to the r equals r times log base a of b. Now all three of these properties come together for a problem like this. We're going to turn this expression into an expression involving only a single log. When I look at this, the first thing I see is that subtraction sign, and I know that two logs that are being subtracted can become one log involving division. The problem is I can't use the subtraction property when there's a coefficient in front of the log, so I have to take care of that coefficient. I need to get all the froggies up on the loggies, so I'm going to take this little 4 and I'm going to have him ribbit right up on top of the 9 there. When I do that, I get log base 2 of 9 to the 4 minus log base 2 of 3. And now I can use the subtraction property where subtraction becomes a single division. So I have log base 2. The first number is always the top number. So it's log base 2 of 9 to the 4 over 3. Now we always want to simplify as much as we can, and you can simplify this many different ways, but one of the nice easy ways to do this is to say that 9 is 3 squared. So we have log base 2 of 3 squared to the 4 over 3. That's going to be log base 2 of 3 to the 8 over 3. 1 3 will cancel out of both the top and the bottom, and that'll leave us with log base 2 of 3 to the 7. Now from here, we could, if we needed to or wanted to, have the froggy jump off the loggy to make 7 log base 2 of 3, but usually the directions will specify that the answer should have no coefficient or no exponent so that you can know which one to give as the answer. Let's try again. Condense this expression down to a single log that doesn't have any coefficients. To get started, the froggies jump up on the loggies. So we have log base 5 of 6 to the 1/3 plus log base 5 of 7 to the 1/2. Now with logs, addition becomes multiplication. So a single log involving multiplication, 6 to the 1/3 times 7 to the 1/2. Now I've done my job. I've simplified this down to a single log with no coefficient. But for this one, if they wanted to be tricky and say no exponents either, that's where we would then say that the final answer is log base 5, have the little monkey swing around and become the cube root of 6 times little monkey swings around, the square root of 7. I can't combine those radicals, and my final answer would just be this right there. Try this one. Simplify as much as possible. Condense it down to a single log. It might be tempting to say that I forgot to write the base on the logs, but we know these are common logs and the base is 10. I don't have to write the base of 10 on a common log. I'm going to have the froggies jump up on the loggies. So I have log a to the 9 minus log b squared. Subtraction becomes division, so I have log a to the 9 over b squared. And that's our final answer. Most often we're using these properties to condense a problem down to a single log. But sometimes they want us to do the opposite and expand a log problem out into multiple logs. Usually the directions would say something like, express this log separately in terms of log base 2 of m and log base 2 of n, or something like that. Let's look at this problem. There are several different ways to attack this problem. It all just depends on how your brain works. As long as you don't break math laws, then your answer is going to be the same no matter which way you attack it. One version looks something sort of like this, where I turn the cube root into a 1/3. Then the 1/3 applies to both the m and the n. And then with logs, a single multiplication will become two separate logs that are being added. And for this problem, let's say that they didn't want any exponents in the answer, so all the froggies have to jump off the loggies. You end up with 2/3 log base 2 of m plus 1/3 log base 2 of n. A different version of this same exact problem might play out more like this. The cube root becomes a 1/3 exponent, and then the froggy jumps off the loggy right here. It's important to know that that 1/3 applies to the entire log. So now when we separate the log at multiplication, and it becomes addition, that 1/3 is going to apply to each log. You'll get 1/3 log base 2 of m squared plus 1/3 log base 2 of n. Now again, if they said no exponents in the answer, this froggy would have to jump off the loggy and multiply to the 1/3, so you'd have 2/3 log base 2 of m plus 1/3 log base 2 of n. Another version plays out in a slightly different order right here. We've got the 1/3 in the front, but then if we have the 2 hop off the log now instead of later, we then distribute the 1/3 to get 2/3 log base 2 of m plus 1/3 log base 2 of n. And again, it's the same answer we found a few times already. All right, let's try one more. Express this log as separate logs in terms of log base 3 of m and log base 3 of n. And let's say that the answer should have no exponents. Here's one way it could go. The square root turns into a 1/2 power. The froggy can jump off the loggy. I know that with logs, a single log that's being divided can become two logs that are being subtracted, and this 1/2 on the outside will apply to both of them. So now if we want the froggy to jump off the loggy here, we have 1/2 times log base 3 of m minus 5 log base 3 of n. And now we can have the 1/2 distribute through to get 1/2 log base 3 of m minus 5/2 log base 3 of n. And there it is. I hope that makes sense. Thanks, guys.